Good afternoon, everyone, and welcome to today's EOL seminar. I am Sarah Woods, if you haven't yet met me, and on behalf of EOL, I'm pleased to introduce Dr. Mathieu Casado, CRNS researcher at LSCE in France. Dr. Casado graduated with both Masters in Geophysical Fluid Dynamics as well as Fundamental and Applied Physics in Paris and Cachan before obtaining a doctorate in climate science in 2016 at LSCE. Dr. Casado has held research positions across France and Germany, encompassing teaching as well as research activities and supervision of graduate students and postdocs. Many of us here today are excited to hear more about Dr. Casado's participation in numerous field campaigns, which have included ice core processing and water vapor and snow isotopic composition monitoring and analysis across multiple campaigns, taking him from France to Everest, as well as several trips to Antarctica. Please join me in welcoming Dr. Casado for his seminar, The Isotopic Fingerprint of the Atmospheric Circulation in Ice Cores in Polar Regions. And a quick reminder for those of you joining us online, you'll find the Slido entry box at the bottom of the screen. Please feel free to enter your questions. Thank you.
Thank you so much. Okay, well, thank you so much for this warm welcome. So it's my first time on here, so it's very exciting to see all those different institutes and people here doing super interesting science and a lot of different things I can relate to, so I was very happy. And I'm going to present some collaborative work between my stuff and also a lot of my colleagues and students. That basically a lot of this work is actually not from me, but some stuff I basically took away from them. And it's going to kind of go around this isotopic fingerprint of atmospheric circulation in ice cores in polar region. And this was a title I kind of made up on the spot when I was asked for a title in an abstract. And I was like, how can I bring this together? Because so far I understand that a lot of you are more in atmospheric science. And I usually try to relate everything to ice core science and paleoclimate. But this is actually a lot of what I do too, and so it was a very interesting approach for me to really take it from the other direction and try to see it from the atmospheric point of view rather than from the paleoclimate point of view. And it actually was super refreshing and helped me a lot. And the idea is, so we use water isotopes as this proxy for temperature in ice core records, but it's not exactly that simple, and I hope that at the end of this seminar, this is something we'll all agree on, that it's more like a proxy of the integrated water cycle, and that this can be used then to reconstruct temperature. And so this is kind of a bit more complex, but I also think more interesting, and this is what I will talk about. And I put this picture of Antarctica because it's always nice, and seeing the snow with the sun like this always makes me think that this is sublimation and fluxes. It's actually snow, but it still works well since I'm measuring the vapor in Antarctica. And again, I start with kind of the traditional aspect, coming from an ice point of view, and I will slowly move upward to the atmosphere. And the idea is we use ice in Antarctica or in polar region in general to kind of reconstruct past climates with this idea that you pile up new layers of snow, and every time you add a new layer of snow, the previous one gets buried, and so the deeper you go, the further in the past you go. And if only you were able to retrieve all those snow layers, you could basically reconstruct past climates. And well, this is actually what we do. When the snow gets compressed, it turns into ice, and we can retrieve it and measure its composition. And so what I'm mainly working on is the isotopic composition, which I will introduce a bit. But there are a lot of other proxies, such as the gas trapped in the air bubbles, but also the dust, the ashes, and even the temperature of the borehole directly can be helping to retrieve past climatic conditions. And so, what are water-stable isotopes? Going a little bit back to kind of make a very general introduction, there are 4 water isotopes that we're using. So H216O, H217O, H218O, and HDO. So changing the number of neutrons on either of the atoms in those molecules. And what is mainly changing in these cases is the mass and a little bit the symmetry. And this will end up to basically change a tiny bit the thermodynamic properties of the different molecules. And this is something that can be useful in geoscience. And again, like a few definitions, so we're all on the same page. We usually speak refer to when we speak about those isotopic composition with the delta value. And for any of you who would not be familiar, the idea is we use this ratio of heavy compared to light water isotopes. We divide it by the average standard ratio of the ocean. And then -1, and we express this in per mil. And so we obtain those three isotopic composition, delta 18O, delta 17O, and delta D. And in polar ice, mainly this would reflect past local temperature variations. So you can see all the three curves here kind of look alike a lot. So at the first order, like they're all more or less similar. And why do we think that they reflect those past local temperature variations? Some people in the 50s and the 60s, so Willy Danchka and Claude Lorius, went to Greenland and Antarctica, retrieved a lot of those like small canisters of snow, measured the average temperature of the snow at those points. And so this, for example, is a US expedition in the 50s. And whenever they plotted all those data points of delta 18O versus temperature, they obtained a very linear relationship to the point that, yeah, if you have a very strong and linear relationship like this, you can imagine this as a thermometer. And so this seems to be very exciting. We have a past thermometer. Then you can still see that there are some very small variations between those three curves. So they were like defined some second order parameters. And I will mention a bit more the DXS than the 17OXS in this seminar, but I used both on a daily basis. And the DXS is defined as delta D minus 8 times the delta 18O. And usually it's used to reconstruct variations of temperature, but from the evaporative regions. And the 17OXS is used as a proxy of humidity from those evaporative regions. And all of those have been used in a lot of ice core papers, and to better or worse of all. And well, everything is nice. We're very happy. We have this isotopic paleothermometer. So this is the EPICA ice core. In black is the delta D, in red the CO2, in green the methane. We have 8 glacial interglacial cycle. And if you look at millennial scale, everything is nice. We have a very nice record, and like there were a lot of super cool papers about this. But if you try to look into a bit more details, there are like a few problems that will come up. And so first one I'm going to talk about today is this kind of isotopic paleothermometer caveat I try to call. And so if, again, like going back to how Lorius and Danchka like imagine this isotopic paleothermometer, they took a lot of samples spatially. So this would be the point in light blue. There was this very nice synthesis from Valérie Masson-Delmotte in 2008. And you get a slope of 0.8 per mil per degree. So if you take all those points into account in Antarctica. Well, you can also like stay at a single space. And like whenever there is snowfall, you take your sample, you seal it, you bring it back to the lab, you measure it. And if you're, for example, at Dome C, you can have a range of temperature from -80 to -20 degrees Celsius. So you have quite a large range. And this is what Barbara Stanley and colleagues did. And here they find a slope of 0.5 per mil per degree. So already we have a problem. Like this thermometer is not super consistent. And this is from the exact same spot in Antarctica. One is a spatial slope, one is a temporal slope. And so like looking at all the spatial slopes across Greenland and Antarctica, we see a relatively consistent isotopic paleothermometer. But if we look into this like in a temporal basis, things are not that easy. We can see, for example, for like different areas, very different values in the precipitation. Then if we look across time scales, we have also like a very large range of values for the delta 18O versus temperature relationship. If we look for different past periods, like looking at all the different Danchka-Oshka events, we have different sensitivities. And this doesn't take into account all the impact of potentially post-deposition processes. And so to kind of be able to really go back into like, why would we have all the slopes? It's a bit important to kind of try to understand where does the relationship between isotopes and temperature come from? And this is where we're actually going back to the atmosphere. And so typically, I have also a video of this, but it's maybe easier to have the slow version here. The isotopic signal captures the temperature relationship throughout the hydrological cycle. And so first, over the ocean, you have evaporation with both equilibrium and molecular diffusion and eddy diffusion that would lead to fractionation and to the vapor being depleted compared to the ocean isotopic composition. And then you have advection of the air masses towards polar region. It gets colder, so it starts to rain and then to snow. And each time you would get preferentially heavy isotopes in the condensed phase compared to the vapor phase. Once you get towards polar region, there is less and less available moisture, there is less and less precipitation, and when the snow falls, you could even have like significant contribution from the exchange between the snow and the atmosphere. And in the end, you get the snow isotopic composition at your ice core drilling site that basically integrates all those different processes. And so it's not necessarily the fractionation coefficient dependency to temperature at this local ice core site that gives you the temperature sensitivity of the water isotopes. It's literally integrating this entire process. And this is actually quite important, and we'll go back to it a bit later. And basically what happens is all of those studies I was showing you here, one thing they have in common, they all rely on precipitation isotopic composition. So it's either snow they got from the ground, either snow precipitation that they got from a table before it touched the floor, could be from ice core. But here, one thing you can also see is the vapor isotopic composition. I mean, it's represented as a cloud, which is not purely vapor. I'm a bit ashamed of this here, but basically the vapor isotopic composition is evolving in parallel with the precipitation isotopic composition. So theoretically, you could study the same kind of spatial studies looking at the vapor isotopic composition instead of looking at the snow isotopic composition as all the study did. And why this was not done necessarily earlier, we need to go back to a bit how we measure isotopic composition. Because there was like a big shift in the early 2000s. So classically, isotopic composition was measured by mass spectroscopy. This is like an example of one of our mass spectrometers in the lab. You have a source that will ionize the molecule. Then you shoot it through a magnet, which will deviate the molecules and sort them according to mass. One small problem with water is that it's an extremely sticky molecule, so you cannot put it directly in your mass spectrometer. So it has to be converted into another molecule. Traditionally, and this is why my lab was measuring water isotopes, what we do is for hydrogen is we convert it, we reduce it into H2, and we use uranium to do that. So this is why this was this lab doing it specifically. And to measure oxygen isotope, classical method is equilibration with CO2, but you can't measure O17 with this case because then the C13 has the exact same mass. And so if you want to be able to measure all the oxygen isotopes, you have to make a fluorination reaction to obtain O2. All those are relatively expensive and very time consuming. So you can only do a few samples per day because of those chemical transfers that needs to happen. But in the early 2000s, like in application of infrared spectroscopy to measurements of isotopes really flourished. And the idea is instead of measuring each molecule by mass, what you can measure is the absorption spectrometer, the absorption spectrometer, yeah. And for each molecule, you will have different transition that will be associated with those absorption areas. And the area basically of each of the transition is proportional to the concentration. So for example, this one is associated to H218O, H216O, and HGO. So if you measure this, you can basically reconstruct the isotopic composition. And like the big impact that this has is not only for the measurement of ice core records, because you can measure a lot more samples. So like for us, when we have to measure several kilometers of ice cores, this is a huge help. It's also that those spectrometers are like light enough, like 20, 30 kilos, that we can bring them to the field, which we could not do before. So now we can actually measure directly in situ the vapor in those sites. We're not the first ones to do this. Like, there have been a lot of teams, and here these are only the time series where people have been able to monitor isotopic composition for more than a year. But there were already quite a lot in 2016, so this is not necessarily new. But since we had access to those very cool polar region sites, and we were able to do this, so for example, at Domcy, at Dumont-d'Urville, quite a few other sites that I will mention. We're also able to do it at Everest, but I'm not going to talk about this today, unfortunately. And so going back to this scheme, basically the idea is we're going to be able to measure the vapor isotopic composition here. And if you're able to measure this, you can think of a lot of different experiments. And so I'm going to try to give an overview. Maybe I'm trying to show too much and not focus on enough things, but it was too difficult to choose. So I will try to make it a mix of, so we can go in a few things in depth and then like maybe go over a few other things quite rapidly. And so then the idea is, if you go to Antarctica and you're able to install like an instrument, you're going to be measuring in the atmospheric boundary layer. So typically our inlets were around 2 meters. And here it's a bit tricky because you have to balance where is the moisture coming from. Because theoretically you can have moisture coming from the free atmosphere and like horizontal and vertical advection, and you can have moisture coming from the exchange with the vapor. And so for the latter, we try to like study a little bit at Domcy. So this is typically how Domcy looks like from a satellite point of view. There is a station that you can see here in the background, and we install our inlets in an underground shelter to have the least effect of the shelter on the turbulence, and to really be able to like, not disturb too much the atmospheric circulation. And dominant wind were coming from here, so most of the time we didn't have any effect of the station. Domcy, typically the average temperature is minus 54 degrees Celsius, and it's 9.5 centimeters of snow accumulation, so it's relatively small for like one of the driest places on Earth. So this means that, for example, the contribution of sublimation and condensation is typically up to 10% of the annual accumulation for this site. So this was like a very interesting site to be able to measure the vapor isotopic composition. And back in 2014, when we did this first campaign, the lower value for like a Picaro instrument to measure vapor isotopic composition was supposed to be around 5,000 ppm. The maximum value we obtained during the entire campaign was 1,000 ppm. So since we were a bit unsure of what to do, and since I was very lucky to be in this lab where a lot of like pioneer of water isotope were working, I was asking them like, how did you used to do this type of vapor measurements before infrared spectrometers? And we basically got out of the basement those huge cryogenic traps that we could basically pump a lot of the vapor, freeze it into a glass canister with like liquid ethanol circulating around it to actually have a comparison to validate our measurements, because we're way out of the range at which those instruments are supposed to measure. And so this is what I'm showing here. In green is the delta 18 of the vapor, and the dark green is the cryogenic trap. So we see, at least for the delta 18, quite good agreement. And then in blue is the DXS, and as I said before, DXS is a second order parameter. And so the very interesting part of this is that if you mess up your measurements, you will see it directly if the DXS is wrong because of those very high sensitivity. So this was like very encouraging as for like all our calibration processes, that we were doing things more or less okay. And then like if we look into more like in-depth on the data, something very funny was happening during this campaign. So here you have more or less a bit less than a month. And for the first 10 days, we have like a little bit erratic humidity diurnal cycle. And we have absolutely no diurnal cycle in delta 18. And Domcy is a site, as I said, where we expect that we have a lot of contribution from the snow. So basically, we expect a strong diurnal cycle of the vapor responding to the strong extremely strong diurnal cycle of temperature, like around plus or minus 10 degrees Celsius per day. And so like we kind of identify those two regimes during our study period. And then the second part, we see that we have those quite large diurnal cycles. So like we try to separate those two regimes. And here, I'm trying to show the average diurnal values for surface temperature and 3-meter temperature in light and dark purple, delta 18 in green, the wind speed and direction in black and like the squarish, and then the humidity in red. And so like you can see basically that the temperature, like the snow surface temperature cycles are more or less equivalent amplitude around 15 degrees Celsius. At 3 meter, we can see that during the first period, we have a reduced amplitude of the cycle. And at this point, we're a bit confused and we're discussing with the meteorologist. And like everyone believes that for sites like Dome C, and this was what we're discussing a bit before, like everyone believes that it has to be convective turbulent situation all the time. It's very sunny, 24 hours a day, wind kind of a divergence in terms of winds, but it's supposed to be relatively well mixed. And what we basically ended up thinking, and there was no sonic anemometers, one has been installed since, but is that to be able to observe absolutely no changes in the delta 18 during the diurnal cycle, we would need to have like a stratification of the atmosphere that happens during like those entire 2 weeks, which were among the warmest days of the year. And this was like extremely interesting for us. And oppositely, during this second regime, we have like changes at the surface of the isotopic composition, which is then like shifted upwards by eddy diffusion, so by some turbulent convective mixing. I can basically show you how a night looks like. Unfortunately, I couldn't put it in my presentation, but typically this is how like the night would look like. And what's interesting is eventually we start to be inside the cloud. So here, this is another shelter, like almost a kilometer away from us, and it really disappears because we start to be inside the cloud. So like all those aspects of vertical mixing that end up with, funnily enough, not something very stratified, just like quite well mixed. And this basically, this was me that you saw briefly because I was sampling some snow sample throughout the night every hour to be able to study the change of snow and vapor at the same time. But this is very interesting because then if you're able to have those very high supersaturation near the surface, and we're talking here like something 130% to 150%, you would expect that you get very strong deposition of snow at the surface. And this was something that we wanted to test isotopically. So going back to the presentation. Typically, during this night, what we observed is we observed this phase of frost deposition. So to observe that, we had a camera that was doing a time lapse on some snowflakes, and we could see them really growing on the floor. And during this change, we observe a change of 10 per mil of the vapor isotopic composition, and at the same time, a change of -2 per mil of the snow isotopic composition. And for this to happen, like we try to make a small like toy model, and you would need to have, you can't have like a purely stratified boundary layer that would be isolated from the free atmosphere, which would represent this epsilon equal 0. You need to have some mixing. You need basically to renew part of the atmospheric boundary layer. Diffusion would not be fast enough to bring the moisture. So this was a very interesting thing. Without a sonic anemometer, it was very difficult to go a bit further. So like we tried to do some bulk evaluation of the fluxes, but the error bars are way too big. And this is something that basically will impact the snow isotopic composition at every time scale. So like just two small examples. Here, this is a paper from Sonia Val, who is going to start a postdoc with us next year, and who did a similar study in Greenland and showed that basically the snow isotopic composition, so the small triangles, is driven, like the change of the snow isotopic composition is driven by the vapor isotopic composition in this period without any precipitation. And here they actually had a sonic anemometer to evaluate the fluxes, a bit better than we did. And then this is another study that we published a bit more than a year ago, where we had almost 4 months with almost no precipitation, which was a bit weird for Dome C. And during this red period, so December and January, we were able to identify that the 5.5 per mil change of delta 18O was purely due to some sublimation fluxes. And then during this February-March period, the minus 2.7 per mil was purely due to condensation fluxes. So really the exchange between the atmosphere and the snow have quite a large impact on the snow isotopic composition, which potential impact for ice core records. But I promised I would stay away from an ice core paleo point of view, at least for now. I will try to keep my promise a bit more. And going back a little bit for atmospheric point of view. Another funny thing you can do is, as I said, when you're, and showed on the video, when you're at Dome C, you can very easily be inside the cloud. So this figure is somehow a little bit wrong. I tried to tweak it quite rapidly, but I didn't have a lot of time, so I just modified. The idea is when you're having your inlet here, you can actually directly measure what's happening inside a cloud. And one very small example was in March last year, there was a huge atmospheric river at Dome C. So typically, this is a simulation from Laboratoire for the event. So Dome C is here. And there were temperature of minus 10 degrees at Dome C in March, knowing that normally the climatology for March at Dome C is around minus 50, minus 60 degrees. So we're talking 40 degrees anomaly of temperature. And we're lucky enough that the instrument was measuring at this point. And so typically, this is how the humidity and isotopic anomaly looks like throughout this atmospheric river. So this is quite a work in progress. We still haven't retrieved the snow isotopic composition that was measured and the precipitation. So this is something that we're going to continue to work on. But it's very exciting to kind of be really in those cloud conditions when there's huge advection period. Unfortunately, those type of events are really rare for Dome C. I mean, of course, those huge atmospheric rivers are really rare, but even normal synoptic event with 10 centimeters of snow per year means that you have very few of them. And most of the time, all the accumulation can be due to 1 or 2 synoptic events per year. So this is something quite dramatic. And so I'm going to try to go to maybe a bit more common sites than Dome C for this point, because Dome C is really a bit isolated. So we've been quite lucky to have quite a few stations near the coast in both the Arctic and the Antarctic. And in these cases, so just a few snapshot overviews, one of our postdocs has been using some data from Svalbard, where we installed a Picaro. We're able to also measure the vapor isotopic composition for almost 3 years. And in this case, very different point of view. Most of the variability of the isotopic composition in the vapor is due to the advection and the regular coming of synoptic events. So typically here, the bottom graph would be the delta 18O, and you can see that every time there is a storm, with those dark bars, there is a huge change of delta 18O. And here, for example, we can see a little bit the diurnal cycle, but this is almost nothing. So this is a very different world compared to what we obtain on the plateau, and very different world to more or less what happened in ice cores. And when I was trying, this is a little bit of a small detour, but when we were trying to think how can we bridge those two things, so we installed also a couple of instruments near the coast in Antarctica. How can we connect the coastal world that we would get in the Arctic and on boat measurements, for example, and what we get inside the continent? So this was actually quite difficult. So here, for example, is another example near the coast. You have the mixing ratios, delta 18O, the temperature, and the wind speed. And what's interesting is the very good agreement for those two sites, which are only 10 kilometers apart, for the mixing ratio and the delta 18O. And what's even more interesting is that it's even better than the temperature. And as I said in the beginning, the common view of water isotope is that this is a temperature proxy. And if, for example, the diurnal cycle here were driven by the temperature, we should have a difference in the two isotopic records from those two sites that are only 10 kilometers away. So here, like with some analysis, we're able to identify that actually the changes of isotopic composition here are purely due to different type of wind regimes. So during this first red period, we had a huge synoptic event, like a huge storm coming to this area. And this is what drives the change of humidity and isotopic composition. And then like this calmed down, and then the change of isotopic composition are purely driven by katabatic wind. So like those dry and warm wind coming from the continent. And in this case, the fact that we have those small difference in temperature for those two sites does not influence the isotopic composition at all. And so again, like this is very contrasting world. And so like we're trying to think like, can we fill the gap? And like there were a lot of campaigns that basically studied the vapor isotopic composition of both around Antarctica. There was the ACE traverse mosaic by the German trying to study in the Arctic. And so we're thinking like, could we actually do this on land? So driving from the coast to inland. And so this is actually when I started to work with Adriana on this very fun project. We went on this traverse with some colleagues from France, Italy, and Australia. So we drove those big trucks across Antarctica, starting from Dumont d'Urville all the way to Concordia, and then to this mega dune site in between the South Pole and Concordia, and backwards. And so what was extremely interesting is for this entire campaign, we had at the same time vapor measurements at DDU and Concordia, and traveling vapor measurements across this traverse. So globally, here as a result, the mixing ratio, so of course it's much wetter and warmer near the coast, and when we traveled, so the orange one is the east traverse, when we traveled from DDU in green towards Concordia, you can see that the humidity directly decreases to almost the plateau values. Interestingly enough, the isotopic composition only reached the value of Concordia's when we actually reached Concordia. So this was really like minimal isotopic composition we got on the plateau. And we traveled and came back. So a lot of things happen, and I'm not going to go into all the detail because it's quite an intense thing. But what I was saying in the beginning is theoretically we could do the same type of studies when we try to compare the spatial slope of isotopic and temperature and the temporal slope of isotopic composition and temperature in Antarctica. So here in orange, sorry the color, we're not very coherent for this talk, but in orange as a surface snow, so the spatial samples that were gathered across Antarctica. In blue as a precipitation sample at a single site, so the temporal slope. And we can see the difference. If we try to like fit a classical Rayleigh model, so the idea is how we try to understand the change of isotopic composition is usually with this type of formula. And the important term here will be this Reinhardt fraction F, which is basically in a classical Rayleigh model just determined by the ratio of saturated vapor pressure across your range of temperature. And typically here, you can easily fit something that would match the surface snow isotopic composition, so the spatial slope, but it's very difficult to fit something, to have something that would fit the temporal slope. You can do the same basically here with the vapor. So in green is the data from DDU from the coastal site, in blue from Concordia. Those are like two temporal variations of vapor isotopic composition, and in orange is the spatial slope. And again, like you can see that you have this relatively high slope, so around 0.81 per mil per degree. And this doesn't, you can't basically have a formulation of this type of Rayleigh models that will fit with the temporal slope at a single site. And so this is how I really spend a lot of time with Adriana and bothering her a lot to try to understand how this moist isotopic framework could work. And in this case, you actually start with the same formula, but instead of having F being entirely determined by the ratio of saturated vapor pressure, you then like use a moist pseudo-adiabatic framework, and you instead would basically follow isentropic surfaces. And Well, this is a little bit of a complicated figure, but bear with me. The idea is then instead of having one type of behavior when you're going to change the temperature, you're going to have to follow two different behavior. And so here's kind of a schematic of all the different isentropic line in Antarctica, so with DDU, the East Traverse, and Concordia. And the idea is, if you're looking at spatial variations of temperature and isotopic composition, so you're going more or less along isoentropic surfaces. So you're traveling basically along a single surface. I mean, of course, it's a bit more complicated in real life than this, but more or less the main variability is you're changing the rain at friction for like a single surface. And basically this would relate in this isotopic composition temperature plots as those dashed lines. But it's very different if you're looking at a single site and you're looking at the temporal variation of isotopic composition. Then what you see is, for example, that summer at Concordia would be on the 2077 isentropic surface, and winter, no, it's actually the opposite. Summer will be on the 2085 surface, and winter on the 2077. Like you go from the light green to the dark blue surface. And this means that basically, in this case, when you change temperature and isotopic composition, you would follow those solid lines. And this might seem a bit kind of a very complicated explanation, but this was actually a very cool way to just add one extra complicated, 1 degree of complexity to the problem. Because like if you just have this simple Rayleigh model, you're not able to get enough complexity to have different behavior if you're looking at the problem temporally and spatially. And here, adding this type of framework was sufficient to understand this and to basically validate that the spatial relation and the temporal relation should be different. And the second point is with those data, we could validate with a single type of data, so with the vapor isotopic composition in both cases, that the spatial relationship and the temporal relationship should be different. Instead of having two different types of data, on the one hand, precipitation, which is like something you capture one day, you put it in a vial and you analyze it later, and surface snow, which is usually integrating, like the way that they were capturing the canister is this is integrating like up to 20 years of snow isotopic composition and measuring the average temperature. So there were like potential reasons that those spatial and temporal relationship would be different just because the samples were very different. And so like just before I wrap up, I wanted to kind of say like, so this is a bit complex, but still very interesting. And I promised I would try to stick to the atmosphere, but I'm still going to make a small like detour for ice core records in particular, because I think it could be quite interesting for a few of you. And I'm going to apply this new basically understanding of the isotopic paleothermometer to an ice core record. And the first figure I was showing you is that basically you can have slopes of all the way from 0.3 per mil per degrees to 1 per mil per degree for the conversion between delta 18 anomalies and temperature anomalies. And this could be very important because here, like in Antarctica, we have very few years of temperature measurements, only like basically 50 years and not even for a lot of sites. So it's very difficult to evaluate the current warming in Antarctica. And there have been like a lot of contradictory studies of whether like we could actually detect it already with meteorological measurements. But if you look at ice core records, like this gives you like a very strong context. So here I stacked 78 ice cores and I have like this 1,000-year context for the current warming. And yeah, again, like it looks like there is like a significant warming for the next year, for the last part of the curve. And so this is like having to put a bit more statistics into this. So typically trying to do something robust in terms of statistics. On the left here, you have this ISO2K stack. This box plot would be basically all the different trends that you can get for the last 1,000 years. So like basically how out of the ordinary would be the current warming from these ice core records. And here, if you have a problem on the conversion from isotopic composition to temperature, this creates a huge uncertainty to the point that you're not sure that you have polar amplification if you have the lowest value, to a huge polar amplification if you have the highest value. And trying to use what we just learned, like using this type of isotopic paleothermometer for Antarctica, what we obtain if we use this temporal slope that we just basically determine would be something that actually corresponds to quite significant polar amplification, would be this red dot. And something which is in line with, for example, the data we obtain in ERA 5, but there's like a lot of controversy with the use of ERA 5 to evaluate the current warming due to the limitation of the satellite data before 1979. And this is basically, if you use meteorological data, it's a bit complicated because, again, we have only those 50 years, and depending how you filter them, it's a bit complicated. And if you compare this to models, then we obtain something that suggests that models, and here this is only SEMIP 5 to use the past 1,000 reconstruction. I will show also the SEMIP 6 later. Models will tend to underestimate a little bit the warming trend for Antarctica. And this is something that meteorologists would be a bit upset about because they tend to agree with the weather station data that says that basically model overestimates the change. And so this was like, can we actually trust those ice cores in this case? And we did a couple of spectral analysis, and we also looked at the decadal variability. And one thing that, again, in the ice core community, we tend to believe is that models tend to underestimate the decadal variability. So here, this would be natural variability at the decadal scale. And then, of course, we have relatively good agreement at a centennial scale, and we have relatively good agreement in the internal scale. And so basically, having both those ideas in mind, like one thing that we were trying to look into is, can this be used as something interesting to try to understand if models would be underestimating the polar amplification in Antarctica? And this is going to be one of my last slides, I promise. And the idea is basically here, this diamond would be ice cores, suggests that most of the model would underestimate the warming trend in Antarctica. So here the blue square would be SEMIP 6 historical runs. The orange square would be SEMIP 5 past 1,000. And the interesting thing, if you include both natural and forced variability and compare to the warming trend, of course, the forced variability will be dominating. And so you have a relatively good correlation between how much a model underestimates both the variability and the warming trend. But surprisingly enough, here you have a significantly robust, I mean, it looks like a patatoid, but still a significantly robust correlation between how a model will underestimate natural variability, so internal variability for the model and natural variability for the data, and the warming trend. And basically, this was something that guided us to think that potentially the reason for which models will underestimate the warming in Antarctica could be the same as the reason for which they underestimate the decadal variability. So I don't have the solution now for how we can solve this, but this is hopefully something that will come in the coming years and would be very interesting to try to improve model at the local scale without harming the good performances at the global scale, which is, I guess, like the goal. And so to kind of conclude and like give a bit of perspective, we have a lot of those field monitoring of water vapor isotopic composition, and we've been trying to use them into a wide range of things. So as tracers in the study of the water cycle, because they're sensitive to phase transitions, so they can be used as tracer in the water cycle. We've been trying to use them to evaluate how the isotopic signal in ice core records is affected by the local exchange. And having this continental traverse in Antarctica was a very cool way to go back to the spatial and temporal variations of the isotopic temperature relationships, and alternative and way to confirm that this was something like a feature of the climate and not a bug from the measurements. Unfortunately, we can't measure in winter right now because it's too dry. And so like, this would be the next step, is to be able to have instruments that are able to measure year-long in Antarctica. And for interpretation of ice core record, like this basically has been super interesting to be able to refine the isotopic paleothermometer and to try to apply it to those 78 ice cores that already exist in Antarctica, and to like look into how both the natural decadal variability and the warming trend has been underestimated in model, probably links to polar amplification feedback loops. So thank you so much, and if you have any questions, I'm happy to answer.
Thanks, Dr. Casado, for that really interesting seminar. I'm not an expert on isotopes by any means, so that was a really nice overview and a lot of fun. Does anyone in the room have any questions?
It's not super related to the isotopes, I don't think, but it was just a curiosity that came up. What are some typical ways to measure snow temperature?
So yeah, typically, like to measure the average temperature of a site, what people usually did is dig a hole with a drill, like 10 meter deep, put the sensor, waited like 1 or 2 days, and because the snow is such like an isolating system, it would basically at 10 meters inside the snow, you usually have the average local temperature. But then you need your sensor to be either very light or so it doesn't basically heat up the snow around it. So that's why like they were leaving it a couple of days.
Okay.
But yeah, porous material are horrible to work with. So like to really measure the temperature of snow, it's really difficult. So yeah.
Yeah, that's why I was curious. Like, so it's through thermal exchange. It's not. I was wondering if people look at the radiation from the snow or something.
So yeah, this is also done. Some of the measurements I showed here, like we use some basically laser measurements, but you need to take several things into account. So you're not going to measure the surface. You're going to measure a couple of centimeters inside the snow, and you need to take into account that you're not measuring a flat surface, and this is a lot of test and calibration, I think, inside the lab to basically, I guess like you will need to generate snow that you know at a given temperature and measure it with the laser system to really calibrate your sensor. Usually like the calibrations that the people selling you the sensor would give you will not work for snow.
Thanks.
When you say you stacked 78 records, you're essentially averaging them all over the same time period, or are you stacking them in time?
Yeah, no, that's fancy way to say we average them.
Yeah.
No, I mean, we removed the value and we average the anomalies. In practice, we would, like, the way that we use data and usually do statistics, we would not have done that. But basically, this is how people in paleoclimate community do it. So basically, it's probably not the best way to extract the most signal from those data. But since this is how people are usually doing it, this was probably the more representative of what was done in the community.
Yeah, I was just kind of curious how much variability there is in between the individual records, and would you ever see that trend by looking at one site?
If you look at one site, you would not see that trend. And actually, water isotopes, and this could have been a totally different seminar that I felt like maybe less described, but like we've been studying like the amount of signal to noise ratio in a single record is less than 1%. And so here, like because we're averaging out 78 records, we're able at a time scale of like around 5 years to get a signal to noise ratio above 1. But if you use like one record, you will not be able to see those trends at all. And this is why it's been very hard to actually start to detect climate change in Antarctica. And when I started actually this study, I was not thinking I would be able to detect it. My goal was to use those data to predict how many more records and when would I be able to detect it. I was not expecting that 78 would actually be enough, because since it's like less than 1%, I was thinking, yeah, square root of 78 would not be nearly enough. But in the end, actually, it was enough, surprisingly. But redoing the math when we had this, like we're able to actually predict that, yeah, this would happen. And one small funny thing, for example, is with this record, we're able to detect the cooling linked to volcanic eruption, for example. So this was something that really convinced us that this was not necessarily artifacts, but that we're able to see interannual variability in those data.
Thanks, Brittany Lease. We have a question online from Jiang. Says, thanks for the nice talk. How can we best compare model, with say a resolution of 100 kilometers, and ice core records at a specific location? Does this imperfect comparison impact their spectral discrepancy?
Yeah, so that's a very good point. So for comparing the models to the records, like we try to take into account the nearest grid point for each record, and this was, of course, like not necessarily perfect. On the other hand, like this is also what was done, for example, to compare model with weather station. And so typically, like the study, for example, from Megan Jones et al. In 2019 in Journal of Climate was comparing the different warming trend from all the semi-PSIX model across Antarctica with the ice core records. And here, overall, like what we kind of claim is that our ISO2K stack, so like this time series, would be representative of the average temperature across Antarctica. So we've compared it to basically different gridded profiles to try to really compare with the average temperature across Antarctica. So in this regard, like it's not necessarily that we're comparing a single ice core with like one model output for like this single site. It's basically we're comparing the average of all those ice cores with basically the average for all those models for like what they predict as a warming for Antarctica. So it's, I guess, like not a single specific location. But the fact that we're taking into account those 78 ice cores that are around Antarctica could have given you a map to show you where all those cores are, but they're really spread out there. Next time I add the map here, might be useful. I don't know if this answers the question.
That's great, thanks. Chris?
Thank you very much for the talk. I was curious, how much variability would you see in your ratios based on both the slope angle and the slope orientation of where you collected? And you know how, as you go down deeper in ice, you don't necessarily know what the slope angle or orientation were at the time of deposition. How much does that affect the results?
I mean, if we were at this level of precision, that would be great. I think like this is like third of the parameters. I think we barely like trying to understand the first order, like the rough temperature to isotopic composition. I mean, we try to measure, for example, isotopic composition on both sides of a sastrugi. So like we're like basically a small snow dune. And like we really had then two kind of angle, but like the spatial variability is so high that you, like for example, this is why we needed to stack like those 78 ice cores. Like if you take profiles from a single site, they're, at least at interannual scale, they don't look alike so much. If you go to millennial scale, everything works super well. Like all those profiles, like you have very high coherency. But then the issue is, on the one hand, the climate becomes more coherent. The number of degree of freedoms at millennial scale are much smaller. So it's both like your record is becoming more coherent, it's becoming better because you're averaging a lot of years, but climate is also becoming more coherent. So you would like to be able to like study how incoherent the climate is at interannual scale, and this is still something I think we're not ready yet. But yeah, maybe in 10 years I can come back and answer your question.
Great talk. I understand looking at temperature anomalies to look at warming and cooling cycles. What is the advantage of looking at oxygen isotopes? From what you describe, it seems like a very labor and expensive endeavor.
Well, I mean, I guess like this figure is perfect to answer. Like in Antarctica, we have no data before 1956 with the year of polar prediction, or I don't remember, like the one that they did in Antarctica in the 50s. So before that, you have no temperature measurement, so you don't know what happened. So I guess one of the big advantages to really be able to go back. I mean, at least in terms of paleoclimate, to go further back in the past. In terms of modern studies, I think it's more interesting to use this as a proxy of the hydrological cycle and to better understand the system. Like a thermometer will win any days. But then like one thing like for the, so basically here we a little bit in between because we have thermometers now, but then we don't have the context. And I think like here the only interesting part is that we have this 1,000-year context that we can put the recent period in to mirror it. So this was kind of an in-between. I think like in 50 years, probably even less, like we won't need ice cores to tell us that Antarctica is warming. I mean, I hope that everyone here was already convinced that Antarctica was warming, but like to actually detect it and quantitatively compare it with model, like it's still like, actually, I wasn't thinking that those reviews were going to be so animated. Like the reviewers are really passionate among themselves, like almost like on which type of meteorological station is acceptable to compare to for the warming. So like there are like papers literally having contrasting like opposite results, like on the warming in Antarctica. There is a paper that claims that the warming is between 0.3 and 0.6 degree per decade in Antarctica, so similar to the Arctic. And there are papers that says with more or less the same weather stations that the warming is at 0.1 degree per decade. So ice core falls kind of in between, and we still have a hard time to convince reviewers that we might have still a larger warming than in models.
Thanks. Any other questions in the room? All right, then I have one. I know for the sake of time, you covered a lot, but you didn't get to talk about Everest. Was there anything surprising or key findings compared to, you had some good contrast between Antarctica and Svalbard. What did you see in the Everest measurements?
So the Everest measurements are very different because it was with a Chinese team which has very high ambitions. We actually had 6 spectrometers at 5 different altitudes ranging from 3,800 meters to 6,500 meters, plus another one that was on a anchored balloon that was going up and down. And so those results are still like being worked on. And it seems to be kind of very interesting because here it's completely different world. I mean, the tropics, of course, would be very, very different. But like, all of this is irrelevant. Like, it's mostly like the signature of the monsoon versus the westerlies that you're trying to identify. And then the question is, how many years would you need to like be able to see a change of atmospheric circulation associated with, of course, all the things that are happening right now? And this is something I leave to my Chinese colleague. I was more like to help them to install the instruments and to help them with calibration, because this is, again, very difficult and very dry and cold. And I guess all the people around you who do experiments knows how calibration can be very finicky in this type of situations.
Great, thank you. Well, if anyone else has any questions for Mathieu, he's visiting till Friday. You can reach out to him or Adriana Bailey. Sounds like you have some really exciting observations that are still in the works, so we'll look forward to seeing how that comes out in the next few years.
Yeah, and you can always contact me even when I'm back in France. And also, like, we have 2 PhD positions that we're going to advertise, like more on the ice core side, but if you have a master students that would like to go in France to do a PhD, you can contact me and I can send you more information.
Great, thanks. Let's thank him for a fascinating seminar.
Thank you so much.